morning, students. In previous class, we discussed about PERACIDS topic, and in which I have discussed about the stereochemistry, of the olefin, and we will continue with the topic. So that is a continuation topic, right? So what I said in previous class, so that is, and near the double bond, suppose if there is any substituent is present, so then we will get the epoxide formation in the opposite direction of the or opposite plane of the substituent. For example, suppose near the double bond the substituent present in the above the plane, then we get the epoxide in the below the plane. And the substituent, suppose if substituent present in the below the plane, then we will get the epoxide in the above the plane, right? And we will continue with that. Already I have explained with one example, right? So that is, again I can give, right? So that is, so this is the double bond, suppose just imagine, and here I have a methyl group in the above the plane. Then if I oxidize with Msc-Iv, then the resulting product, right? Near the double bond, the group is present in the above the plane. Then the epoxide formation takes place only from the below the plane. Why? Because below the plane having sterically less crowded part. So that's why here epoxide formation takes place from the below the plane. Got my point? Right. And here, so the product is, so the major product is from below the plane only. Why? Because in above the plane the substituent methyl group is present. So that's why here there is some steric crowding between the reagent Msc-Iv and methyl group, right? And so that's why here this product is major. And also if we can write one more product like this, so that is from above the plane epoxide. So this is always the minor. This is minor, right? So whenever we have major and minor, then we can say the reaction is stereo. Then the reaction is stereoselective reaction, and what we are discussing, stereo selectivity. What we are discussing, stereo selectivity. In the same manner, suppose if you take one more example, that is here I have taken an olefin here, but near the double bond there is some methyl group, but here in this case the methyl group present in below the plane, right? So that's why here whenever we use Msc-Iv, then what is happening? Then automatically the epoxide formation takes place from above the plane. Why? From the above the plane. Why? Because here below the plane having steric crowding. So below the plane having some steric crowding. So that's why here the major product is only from above the plane. Only from above the plane. So this is the product. So this is the only major one. So this is already in previous class I have explained this application. Again I will continue with this application, right? So simply what you have to understand is that, right? So if near the double bond, if there is any substituent present, not only methyl, you can take ethyl or propyl or any kind of substituent. Near the double bond, if substituent is present, definitely we can expect the opposite stereochemistry to the corresponding substituent. So this is the point you have to understand, right? Next, right? Suppose in the same manner, I just want to give you one application here, right? So that is, suppose I am taking one more application here, and double bond, and some OH group is present near the double bond, and here OH is the substituent, but here methyls are the substituents. Got my point, right? And here whenever I use MCPBA, whenever we are using just MCPBA to oxidize double bond, then what is the product in general, what we can expect automatically? So we can expect the product, that is epoxide formation taking place from the below the plane, but here the product is not like that, and here surprisingly we got some epoxide formation from the above the plane. Did you observe this, right? And here you have seen, okay, actually what we have to expect is that we can expect the epoxide formation from the opposite plane of the substituent. In spite of that, what we are getting here, so we are just getting the epoxide formation in the same plane of the substituent. How it is possible? Yes, of course it is correct. This is the right answer. This is not wrong answer, right? But it is correct. How it is correct? Right? Why the product formation taking place like this? Right? But here, so this is because here the substituent is polar group. Right? This is not a simple group. This is polar group. Right? This is polar group. Right? So whenever polar groups are present near the double bond, then the epoxide formation taking place in the plane which is concerned to the polar group. That is, if polar group present in the above plane, you can get the epoxide in the above plane. If polar group present in the below the plane, you can get the epoxide formation from the below the plane. That is happening. Why it is happening? So that was explained by the scientist Hebest. That was explained by the scientist Hebest. Hence we can say it is Hebest epoxidation. What is the name? What is the name of this one? Hebest epoxidation. Got my point? So this is Hebest epoxidation. Hebest explained why we are getting the same stereochemistry whenever the polar group is present in the same plane, whether it is above the plane or below the plane, then why we are getting the same, the epoxide formation is also taking place in the same plane, why we are getting like that. So that was explained by the scientist Hebest epoxidation. And after his observations, he came to know one thing, that so what is happening here? So whenever polar group is present, before oxidation with olefin, OH group will capture the MCPBA, right? And here the epoxide formation, before epoxide formation, MCPBA is reacting with the OH. MCPBA is coordinating with the OH, which means that so OH, the polar group OH, in this case OH, okay, so will catch MCPBA. So then so whenever it is catching MCPBA, after that, so it is delivering from its plane only. If it is present in the above the plane, so from the above the plane the oxygen will be delivered. So the oxygen means that, so from MCPBA we get only nascent oxygen. So did you understand that? So what is the reactant species here? So MCPBA is a source of nascent oxygen. Nascent means that single oxygen atom, right? So nascent means the single oxygen atom, right? From MCPBA delivered nascent oxygen atom. But so this delivering of oxygen can be decided only by the polar group. If polar group present in the above plane, then from the above plane the nascent oxygen is coming. If polar group present in the below the plane, from the below the plane the oxygen will be delivered. So let me show that. Okay, let me show some mechanism for that, then we can easily understand that, right? And here, suppose here I am writing some mechanism here, right? Hebest epoxidation. Suppose this is double bond and this is polar group again, and so MCl, right? MCl C4H4. Okay, C4H4, metachlorobenzoic acid, right? So MCPBA means metachlorobenzoic acid. Here I am not writing the complete structure, right? So whatever it may be, simply it is a peracid. So whatever it may be, so whether it is MCPBA or simply any kind of peracid you can take, but the mechanism is same, right? And here, so whenever actually when it approaches, right? When the peracid is approaching to the olefin, then what is happening? So before the oxygen is reaching to the olefin, but there exists some intermolecular hydrogen bonding between hydrogen and C double bond O. Why? Because so intermolecular hydrogen bonding. Why intermolecular hydrogen bonding here? Because hydrogen has delta plus character and this oxygen has delta minus character. In the same manner, if you take this oxygen atom, right, it is also having delta minus and delta plus here, right? So between delta minus and delta plus, got my point? Between delta minus and delta plus, so there exists some hydrogen bonding. That means that so this hydrogen is completely attracting the peracid group, right? So that's why whenever peracid is approaching, whenever some polar group is present near the double bond, then it can easily capture or it can easily catch the peracid into its plane. So after catching, so from its own plane only it is delivering. That is the process here happening, right? So that's why here, so this oxygen atom will be delivered only from its plane, so who are directing here? So who are directing the stereochemistry here? The polar group. So polar groups are directing the incoming stereochemistry of the epoxide formation only. So that was observed by the scientist Habast, right? So there is no problem if there are no polar groups are present. As usually you can expect the epoxide formation or the stereochemistry of epoxide formation depending on the steric crowding. But here whenever polar groups are present, it doesn't depending on the stereochemistry, it doesn't depending on the steric crowding, but depending only on the polar group, right? So that's where here, so this entire group is attracted by the OH group and from this plane only it is delivering. This is the process so observed by the Habast scientist. In the same manner, suppose even if you have taken one more group here, what are polar groups? So here OH is polar group. In the same manner, if you have taken near the double bond, NH2 is there. So and here it is also a polar group. So this is also a polar group, right? So this is also polar group. Then, so whenever we do oxidation with the MCPBA, so then what is happening? Again, we get the epoxide formation only from the above the plane. So that is we get epoxide only from the above the plane. Why? Because so if because here NH3 is also present in the above the plane. Unlike that, suppose it is present in the below the plane. Suppose here I am changing the plane, right? So I have placed the NH2 from the below the plane. Then we will get below the plane epoxide, right? If it is present in the above the plane, you will get above the plane epoxide. If it is present in the below the plane, you will get the below the plane epoxide. The difference, right? And here one more example here, and here I am writing one more example taking on this, right? And here suppose I have a group like this, and I have some ester group here. So whenever I use MCPBA, right? So then, and here, but this polarity, this is not a polar group. Remember, this is not a polar group. And here suppose substituent, and here some ester. I have taken some ester, O C double bond O CH3, COO some ester group which is present in above the plane. And here ester is not a good polar group. It is not a good polar group. So why it is not a good polar group? Because so this polarity always is in conjugation. The polarity will be reduced by the conjugation, right? And here the polarity is reduced by the conjugation with the C double bond group. So the lone pair of electrons on oxygen atom again is in conjugation with the double bond O. So in that process it is not a good living group, good polar group. So that's why here the resulting product is right, and here we should consider it as a sterically crowded group, right? Whenever it is not acting as a polar group, then we have to consider it as a substituent. So that's why here what is the resulting stereochemistry of this olefin? So that is from the above the plane epoxide, from the below the plane epoxide. So in above the plane some sterically crowded group is present. In above the plane some sterically crowded group is present. So the epoxide formation taking place from the below the plane. Remember, this is not polar group. We have to consider it as a just like methyl group, right? So that is the difference, right? So I hope you can understand what is the meaning of reverse epoxidation, right? So simply once again I recall. So what is the meaning of stereoselectivity? So the reaction in which if you get two unequal amounts of structural isomers, then one is the major product, another one is the minor product. So that is called as stereoselectivity, right? So in discussing about stereoselectivity, when we get such kind of stereoselective reactions, whenever some substituents are present near the double bond, then we get some stereoselective isomers or some stereoselective products, right? And in this case also we need to remember one point. So is the substituent is polar group or not polar group? If it is a polar group, then you have to consider it as a Hebus epoxidation. If it is not a polar group, then you have to consider it as a sterically crowded group, right? So these 2 points you need to remember, right? Next, suppose beside these compounds, when we are discussing about rigid systems, suppose if you take rigid systems, right, then what kind of product we can expect, or so how the epoxide formation taking place in case of rigid systems? That is explained. I just want that is explained by taking one example. Suppose NAR-borne, okay, just like that, rigid systems. What are the best examples of rigid systems? NAR-borne, right? And here let me take NAR-borne. Suppose here I have taken some rigid system, that is NAR-borne, right? So this is the NAR-borne structure, right? And here we cannot say above the plane, we cannot say below the plane, okay, stereochemistry. We cannot say above the plane or below the plane. So whenever we are taking bicyclic compounds or tricyclic compounds, then we use only, so whether the product is exo or the product is endo only, right? So then we have to use 2 names here. So exoisomer or endoisomer, which is major, which is minor. Okay, up to now here, in case of only monocyclic systems, then we use only above the plane or below the plane. But in case of rigid systems, we should not use such kind of notations. We have to use only exo or endo notations, right? And here, so what is exo? Exo is always stay away from the ring. Endo is always nearer to the ring, right? And here in this system, what we can say, this is called as crowded part, so this part is called as cavity, and so this part is called as cavity. This part is called as cavity. Cavity means crowded part. Cavity means that crowded part, right? Cavity means that crowded part, right? And here, so whenever we are using MCPBA, metachlorobenzodic acid, now you can deliver the oxygen atom either from exo direction or from endo direction. So this is endo, right? So this is endo and this is exo. Okay, if oxygen is coming from this direction, then it is called as exo. If epoxide coming from this direction, then it is called as endo. And this is endo direction is always having some steric crowding, right? I will explain how it is sterically crowded part, right? And here I need to write two possibilities, okay, for this conversion, right? And here I'm just taking two possible conversions. Those are, one is exoepoxide and one is exoepoxide and another one is endoepoxide. I just want to write those two, right? Suppose here I'm writing exoepoxide formation. So this is called as exo. And here again I just want to represent another structure, that is endo. So how do we have to write endo? And let me take endo. So that is like this. Okay, and this is the structure of endo epoxidation right here. But among these two, which is major, which is minor, that is we have to understand, right? So what do you think? So is there any questions? So what do you think? So do you know any answer for this one, which is major, which is minor, right? And here, so simply if you want to answer for these questions, you have to write one question or you have to look for one answer. So that is where we have steric crowding. If you can find the answer for this, then you can easily, so that will be the actually answer, right? So if you can find where the steric crowding is from, steric crowding is present, automatically epoxide will not be approaching from that direction, right? And here, suppose if oxygen is approaching from this direction, then here we have two hydrogens. This is 7th carbon, right? And this is 6 member ring, 1 2 3 4 5 6, and this is 7th carbon. So 7th carbon, at 7th carbon we are having two hydrogens. Suppose if Msc-Iv approaching from this direction, there is no steric crowding between oxygen and between oxygen from the exo and hydrogen at 7th group, there is no steric crowding, right? What we can say? So these are okay. So no steric crowding. There is no steric crowding between these two, right? Suppose if oxygen is delivered from the okay endo direction. Suppose here Msc-Iv is coming like this, right? And oxygen is coming like this. Then whenever oxygen is coming like this, these hydrogens and here these two hydrogens will restrict the incoming oxygen with its Msc-Iv structure. Right? Here steric crowding is not only between hydrogen and oxygen. Oxygen is coming from the Msc-Iv. Remember, oxygen is coming from the Msc-Iv. So that's why here we have to consider. But here I am not writing the complete structure of Msc-Iv. But I'm just showing only, so from where it is coming only, right? So there is some steric crowding between oxygen, this is oxygen and hydrogen having so more steric crowding. This is more steric crowding. This is, so that's why, so these two hydrogens will oppose the incoming oxygen from the Msc-Iv. That's why, so an endo approach is not favorable one. So that's why we get this is the minor. This is endo epoxide. This is endo and this is minor. This is the minor. And so here there is no steric crowding, and the steric crowding is there no steric crowding, or the steric crowding is very less. So that's why, and here okay, so this product, okay, so from this direction only. So this can be, okay, considered as exo, and exo is the major. Exo is the major. So like that we have to explain the stereochemistry of the rigid systems, right? And suppose if you have suppose in place of hydrogens, if you replace in place of hydrogens if you replace by any two bulky groups, any two bulky groups, here hydrogens are small in size, that's why there is no steric crowding between hydrogen and oxygen. But in place of that, you are just taking some methyl group here, CH3, again CH3 here, right? Here I have taken CH3, some methyl group here. So in this case, if you oxidize with Msc-PBA, if you oxidize with Msc-PBA, then what is happening? Suppose if Msc-PBA approaching from the exo direction, so that's why, so between oxygen and the methyl group, entire methyl group, so between oxygen and so entire methyl group, oxygen and entire methyl group, so more steric crowding. So there is more steric crowding, more steric crowding. So that's why there is more steric crowding. So that's why here, okay, exo approach is not favorable, right? So so the epoxide approaching from the exo direction is not favorable whenever some methyl groups are present. So in this case, we are getting CH3 and CH3 and epoxide, but so exo epoxide, this will become minor, minor. This is minor. Then what is major? Endo is major. Endo is major, and here endo is major. So you can ask, but in endo, you can ask these two hydrogens, so restrict incoming oxygens. So you may raise this doubt. But when compared to this steric crowding, this steric crowding is less. Okay, so this steric crowding is having less steric crowding. This is having less steric crowding. That's why when compared to this one, so oxygen is always looking to approach from the endo direction in this case. Why? Because when compared to this one, here we are just having less steric crowding. So like that we can decide whether it is exo or it is endo. So obviously here the major product is endo. So can you understand, students, right? So these are the points, these are the key points we need to remember while doing oxidation of olefin into epoxidation, in which we can explain the stereochemistry like this, right? So all this is stereochemistry is very, very important, especially for second MSc students, right? The stereochemistry is very, very, very important. So this is not only important for examination point of view. So if you want to prepare for any competitive examination point, just like a CSIR or NET, right? So in those competitive examinations, they will ask these questions. Okay, and those questions are related to this topic. So that's why this topic is very, very important, right? So that's why here I am stressing more and more about stereochemistry. So why I am stressing? Please understand, this is not only important for examination point, also important to the competitive orientation, right? Next. So having all this knowledge, again we are just moving to the next topic here, right? And up to here I have discussed so the epoxide formation with only peracid. Suppose unlike that, do we have any other reagent to convert the epoxide, to convert olefin to its epoxide? Do we have any other reagents? To convert olefins into epoxides? Okay, except MCPB or perbenzoic acid, metachloroperbenzoic acid or parasitic acid, whatever it may be, simply peracid, right? But here, suppose there are some more reagents are also present here. So and here hydrogen peroxide, hydrogen peroxide. This is peroxide. Remember, don't get any confusion. So peroxide and peracid is different, right? So in peracid we have 3 oxygen atoms. So in peroxide we have only 2 oxygen atoms. That is the difference here. And we know that H2O2 structure relation O linkage. So this is O linkage here. We are just having. This is the structure of hydrogen peroxide, right? And here, even if you have double bond, but especially when we are using H2O2, right? So whenever if compound having if compound having if compound having if compound having conjugated double bond, conjugated double bond conjugated double bond, then use H2O2 only. Then use only H2O2. So why do we have to use H2O2? Why don't we use Msc-Iv? So we will explain by taking one example, right? So that is, suppose here I am taking an olefin, but this olefin is in conjugation with C double bond O. So that's why here this conjugated double bond, CGB means conjugated double bond. This is not a double bond, so this is called as conjugated double bond. Why? Because this double bond is in combination with the C double bond O. So we are taking conjugated double bond here, just like that, right? And here, so this conjugated double bond always acting like alcohol. Why? Because whenever we are moving pi bond towards C double bond, then automatically we get positive charge here. So that's why here electrophilic character increases. This is not nucleophile. Suppose if you take double bond having some CH3 here, so this is electron rich component. This is electron rich component. The electron density increases on the double bond. So that's why here the electron density increases on the double bond. That's why here this is having more nucleophilic character. This is having electrophilic character. This double bond is having electrophilic character. That's why it is less reactive. It is less reactive. Okay, this is the point you have to remember. Then whenever we are using hydrogen peroxide, in the presence of some basic medium, right? So then we get epoxidation only. Double bond is converted to epoxide along with C double bond O R. Right? And here, so what is the mechanism here? So first, what is the mechanism here? First take hydrogen peroxide, and with the help of base, so H plus ion is deprotonated from here. So with the help of base, what is happening? So H plus is deprotonated. So then we get peroxide ion. So that is O minus plus H2O. This is the first step. Now, so it is reacting with the starting material, that is reacting here. So that is double bond O and R. Now, this O minus and OH attacking only at alpha and beta of the conjugated double bond O. So then this bond is shifted toward carbon like this, and this bond is shifted toward oxygen. Then we get double bond here and OH here, and double bond here, and O minus here, and R, right? And in that process, so and here next step what is happening? O minus again reconverted to C double bond. This is enolate anion. Enolate anions are always unstable. I already told you in so many classes. So that's why here, so enolate anion is unstable. It is reconverted to keto form. So that's why in that process here you will get so negative. This negative is O plus. Why? Because OH is eliminated as OH minus. If OH can break this bond and if it is eliminated as OH minus, then you will get positive charge on O plus. But we should not represent any positive or negatives here, because they will not give any time to do this kind of process. So they won't take much more time, okay, to do this. So that's why, so here it is taking place within a fraction of seconds, just okay, one step. So that's why here we should not write any O plus here, but we have to understand like that, right? What is, so here when the bond between oxygen and oxygen is breaking, so it can be eliminated as OH minus. Okay, these sigma electrons will be taken by the oxygen, OH minus. Then you will get positive charge here, and this is minus. So this pi bond is attacking on oxygen. So then finally, okay, we can complete the product. So that is C double bond OR, and this is the oxygen. Now there is a bond between this carbon and oxygen. This is the epoxide formation. This is the epoxide formation, right? And so this is the mechanism. So how do we have to convert olefin into epoxide? For that, this is the mechanism. Let us see. Same, if we use Msc-PBA, then why don't we use Msc-PBA, and why don't we involve Msc-PBA in the same mechanism? In the same mechanism, but that is not possible here. Why? Because, so even though if it is possible, you will get very low amount of yield. So means that happy for that. If you use Msc-PBA, so you will get only low yield, but with H2O2, you will get a high yield. Okay, you can enhance the yield of the product here with H2O2, right? Let us see why with Msc-PBA it is not possible, right? And here in this case, whenever we use Msc-PBA, metachloroperbenzoic acid, and here Msc-PBA will not show any interest to react with this double bond. Why? Because, and here Msc-PBA acting as a good electrophilic reagent, and here it is delivering only nascent oxygen. Remember, don't forget, it is delivering only nascent oxygen. This is called as nascent oxygen. Nascent oxygen means that single oxygen atom, right? And it is having more electrophilic character. But here, so for electrophilic character, it requires nucleophile. For electrophile, it requires nucleophile. But here, so this double bond is not nucleophilic. The tendency of nucleophilicity will be decreased by the C double bond over here. So that's why here it is a, so this double bond is having less nucleophilic character. It is having less nucleophilic character. Okay, less nucleophilic. This is not nucleophilic double bond, having less tendency of nucleophilic. Why? Because this double bond is shifted toward, then you will get positive charge here. So that's why, so the nucleophilic character will be decreased with C double bond more. So, and here oxygen and Msc-PBA having more electrophile here. So this is electrophilic character. Here it can generate electrophile. Electrophile will not react. Even if it is reacting, you will get only less amount of it. So that is the reason why it is not, okay. So why it is delivering only less amount of it. So but it is reacting with the C double bond O, right? So it is giving less amount of yield with the double bond. Besides that, so it is giving more yield with the C double bond O. With C double bond O, what kind of product we can get? We can get Baeyer-Williger oxidation. What is Baeyer-Williger oxidation? Carbonyl compounds are converted to esters. Okay, in the presence of PERACIDS, so in the presence of PERACIDs, the carbonyl compounds will react with, okay, carbonyl compounds will react with PERACIDs. Then we will convert the carbonyl compound into ester. So this is the major drug. Okay, and here, so what is happening? C double bond is converted to. So this nascent oxygen atom, take a look here. This nascent oxygen atom come here. So this nascent oxygen atom come here, and complete this product. C double bond O, OR. So that's why here what is happening, whenever we are using MCPBA, it is giving bare Villiger oxidation. It is giving bare Villiger oxidation. Bare Villiger oxidation. So this is the measure. This is the measure. This is the measure with MCPBA. That's why. But we don't require this product. What we need, what we want to convert it into epoxide. We want only epoxide formation. But I want this. But if you use MCPBA, you will get epoxide. But that is minor. If you use MCPBA, you will get ester. That is major. That is major. Right? So this is about okay, difference between whenever we are using H2O2. So when we have to use H2O2, whenever there is conjugated double bond. For example, if you take one more structure like this, okay. For example, if you take one more structure like this, right? Suppose we have a cyclic conjugated double bond O, right? Then we should not use MCPBA. Instead of that, what we have to use? H2O2 for getting epoxide. For getting epoxide, we need to use H2O2 but not MCPBA. With MCPBA, we get ester. We get ester. So that's why here, whenever we are using okay H2O2, so then it is converted, double bond is converted to okay epoxide with high amount of yield. Okay students, so this is about today's topic. I hope you can understand. So even if you have any doubt, so please keep in touch with me with WhatsApp, right? So you can raise your doubts with WhatsApp group. Already we have some WhatsApp group there, so college group there. So that's why. So here you don't worry about any doubts. Even if you have any doubts, then you can contact with WhatsApp directly, WhatsApp, or you can call me also. Already my number is also present at you, right? So this is about online classes. Please don't get so because of COVID situations only, we are not we are unable to teach you directly. So that's why we are just planning through online classes only for the PG students. So that's why here I hope you can utilize this online classes. So I hope you can easily understand the concepts that what I have taught right now. Thank you.